Alright, you are welcome back again to this lecture. We are going to look at a normality check. Don't forget, like I explained previously, that normality is one of the assumptions of a parametric test. So because we will be going to parametric test gradually in the next couple of classes, but we want to understand first that parametric has assumptions, and one of them is called normality assumption of normal distributions. That's one of them. So we have what is called homogeneity of variance, and we have outlier checks. So all these ones are very important. That's why I divided the teaching into two parts. One part dealing with introduction to normality check, looking at it graphically. Then the other part we deal with it by writing the code using how we can practicalize it. So we want to understand the background first of data and normality. As someone working on data, you must understand the kind of data you are working with. Sometimes this has been a challenge so far for many people. They don't know the kind of data they are actually dealing with. They collect the data, but they cannot actually differentiate between one data and the other. So when it comes to testing, they don't know which data to use for testing. All right, so let's look at this briefly. I want to start by looking at type of data. All right, type of data. We have different types of data. Okay, from this chart, you can see that we have categorical, we have numerical data. The categorical data is otherwise called qualitative data, which deals with which based on descriptive information. Okay, while numerical data, otherwise called quantitative data, which is based on numerical information. So then that means you have numerical information, countable, and we have also descriptive information, describable. All right. So in the categorical data, you have nominal and you have ordinal. So the nominal data, otherwise called unordered data, it is not ordered. All right. It is data that is not ordered. That's why I call it nominal. And then we have what they call the one that is ordered, that is called ordinal. That other one is ordered. So when I say nominal or unordered data, it's variable which data assume unordered form. The form in which data comes is unordered. Don't forget that algorithm data have different examples which I'll be showing us later. But the data or the column in that field or the variable is not ordered, typed. Maybe in a variable on your data, you have a particular column there called gender, for example. Gender is male or female, or female and male. So it does not have any particular order. That's what it means, that unordered or nominal. So no particular order. Male could come first, female could follow. So we have also example like maybe color. For example, color could be blue, green, red, green, blue, brown, yellow, green. So no order. No one. Let's say this one comes first before this. No, that is what it means by nominal. All right. So we call it nominal variable. Okay. So there are many other examples there too. Other examples that you would like. But when it now comes to ordinal variable data with proper order, it has a proper order. Okay. For example, you can have maybe size. For example, I have short size, medium size, or long size. Okay, maybe you call your variable size. For example, is it short, Is it medium? Is it long? So this one has order. Short come first, medium follows, and long follows. So, or you have another variable in your data set called maybe education level. Education level, for example, you say maybe a column name or variable name in your data set. You have high school, okay? You have bachelor's, you have masters, you have PhD. That's an order. That comes with order. All right. One high school comes first, bachelor follows, masters follow, PhD follows. That's order. Maybe, or you have a rating in your, let's say it's called rating. Sophie, okay, you have a rating. So you have poor, you have fair, you have good, you have excellent. Right? So poor comes first, followed by fair, followed by good, and excellent. These are ordinal. They have order, even though they are categorical data, right? Categorical data, they are not necessarily numbers data. They are just basically descriptive values. Okay, they are not numbers. So they have different categories, but they are ordered because they are ordinal. So when you just look at the word ordinal as order, O-R-D, order, ordinal. So it will help you to understand. So you can have for example something like a Likert scale. You know what they call Likert scale? Likert scale is common when you're dealing with maybe some kind of a survey collection using under management, social science. You have to collect data using survey. So in that case, you use what they call Likert scale. Likert scale can be 7 scale, can be 5 scale. For example, if you have something like 5 scale, you have a strongly agreed, disagreed, neither agree, or disagree, or disagree, maybe agree, strongly agree, for example. So you can have like a 5 scale, okay, like that. So, but it is orderly. It comes in order. Strongly agreed, disagreed. You can have neither agreed, or can have also called strong. You can have also called agree or strongly agree. So these are just language that you use. There are many more other examples of Likert scale that you can point to, but I'm just looking at it from this perspective. All right. So we also have what they call non-numerical. We have discrete data. So this is a countable data. Maybe just like maybe you want the number of children, number of car in the garage, the whole number of students, number of children in the house, number of students in the school. All these kind of things, they are just a normal data. They are called discrete data, right? They are different from another data called continuous, right? They are different. So in the continuous, they are measurable data that I can measure. They are common data that we use in your statistical analysis. I mean, continuous data is a common data. In fact, they are required. You have to measure data. Data must be measured, right? So you need continuous data a lot to perform, especially when it comes to parametric testing. So we have something like height, width, length. You have temperature, you have mass, you have energy, speed, area, sales in dollars, blood pressure, has your PB, cholesterol level, distance, minimum wages, salary. All those ones, they are measurable data because salary is a money that is measurable in the currency, maybe US dollar. So depending on the currency you are using to measure it. Okay. So they are called continuous data and they are very important. So you need to understand them. All right. So we also have, when you look at this data structure, you can see that you have gender here, right? This is called categorical variable. Don't forget that this is categorical variable. All right. You also have age group here. This is also categorical variable. Now, in categorical variable gender, we have 2 groups, male and female. That's only male and female. That is 2 groups. Take note of groups in the categorical data. This one we have 3 groups here in each group. We have adult, we have child, and we have elderly. 3 groups. So groups need to be understood, especially when you are dealing with testing, because there's a group the number of groups that you need to test for ANOVA. but we will to you for t-test. So if you don't know the number of groups you have in your categorical data, then you cannot perform tests properly. So that's why I'm trying to present this first before we go to those areas. So you have gender now, can contain only 2 groups. Okay, you have age groups containing 3 groups. All right, this I call categorical data. Okay, so we also have a continuous data here. That's the numerical data. Both of them are continuous because they have measurements. They are measurable. That's what it means. Height and weight. All right. So take note of that before we go further. So if this is clear, then it means you are able to start your work and to do a proper analysis. So then when we now talk about normality testing, we're trying to say that we want to test our data if it's normal, if it follows a normal distribution. I mean, the sample that data come from a population that approximately follows a normal distribution. That's what we are saying. So, and one of the things we use to check under normality is called skewness. Skewness, that's one of the things. We want to look at how skewed the data is. Is it left skew or right skew or normal? So skewness is a statistical measure that assesses the asymmetry of a probability distribution. It quantifies the extent to which the data is skewed or shifted to one side. So we have a left skew, we have right skew, and this is normal. This is how data supposed to be to assume a normal distribution. This bell shape, all right. Don't forget we still have other like a interference and the rest of it. At least this is very important. The first one, right? Okay. If you look at this, we see this one is left skew, all right. Left skew. In the left skew data, the more you can see the structure here: mode, median, mean. In fact, mean and median is very important, okay, because they are the usual measure that we use, mean and median. So it means more points on the right side and tail leading to the left side, right? This is the more point on the we have more points on the right side here, but tail leading to the left side. That's what you call negative skew or left tail. You can call it left tail. So this is the tail in the left. Okay, skewness value is less than 0. That's what it means. It's negative. There's a negative part. And the outliers are present on the left side of the graph. That means in this left side, there are outliers here. In other words, median is more than mean. Alright? Median is greater than mean. Okay? So, likewise, you can have a positively skewed one, which the other way around, the more points on the left side and tail leading to the right side. Skewness value is greater than 0. This time around, greater than 0. Outliers are present on the right side of the graph. That's what it means. There are little outliers here in this side. Okay? Mean is now greater than median. You can see that it has changed. Mean is greater than median. So that is left skew. But we have a normal distribution which is symmetrical. This is symmetrical now. We have 50%, 50% here. And in this case, mean is equal to median equal to 0. Sometimes mean may not equal to median, but mean may not equal to 0, but mean should be equal to median. May not necessarily equal to 0. Sometimes you can have other number here, but at least mean must be equal to median. So this is called normal distribution. The skewness value is 0 at this point, and there's no outliers. So that is that, and you can see that at the skewness of the data. Okay. So we also have another one called kurtosis. Kurtosis is a probability theory we use to use excess kurtosis to compare the kurtosis coefficient with that of normal distribution. So we look at how shape of that particular bell shape look like. Okay, how it look like. We have what they call positive kurtosis, we have negative, we have normal distribution. So positive one is called leptokurtic, and the negative one is called platykurtic. We have normal, which is called mesokurtic. So that is how the shape look like. So we can have the same thing for there. If it's positive, the degree of thickness is more, which is called every tail, or in that case we have more outliers. Okay, kurtosis value is greater than 0 at this point. When negative, the degree of thickness, the pickedness is less. Short tail, or we have few outliers. Kurtosis value is now less than 0. But normal is symmetrical, median equal to mean equal to mode, and kurtosis value is 0. So the main difference between skewness and kurtosis is that the skewness refers to the degree of symmetry, whereas the kurtosis refers to the degree of presence of outliers in the distribution. So there is a necessity to transform the skew data to be close enough to normal distribution, at least a little bit. All right. So we also have a box plots also help us to look at the shape of our data. The shape of the box plots show that how the data is distributed and also show any possibility of outliers, right? Any data at the outside this particular whisker is the outlier outside this. Okay, so the contours show basically 5 components here. We have minimum, we have maximum, we have lower quartile, we have upper quartile, and we have median. Okay, so that is what. So we have what we call interquartile range (RQ). So this is the future interquartile range. So this is what it shows. So we will explain more about this later. All right. So box plot is one of the graph charts also that we use to also test for normality, how data is normally distributed. You can see that a box plot carries a lot of information. Even though as small as that plot is, it carries so many information. In the box plots, you can detect the outliers very easily. If there's an outlier in your data, you can see the median, the mean, you can see the skewness of your data, you can see if the data is left skew or right skew or symmetrical. So you can know from the screen and you understand that this particular one, you can see that the data, the first one is negatively skewed. Why? Because to the side here, you can see skew long. This one is long. This whiskey from here is long. But median towards the top of data, that is if you take like this, median is greater than mean, and the upper quartile is smaller than the lower quartile. It's upper quartile. So we also have the one that is no skew, one that has no skew. The one is symmetrical in nature. Median is in the center of the data. It's the median, right? And the median equal to mean, right? Median and mean they are equal, and the upper quartile is equal to lower quartile. This upper one is equal to lower one. So, but in the right skew or positive skew, you can see that the median towards the bottom of the data. So we assume that this one, this is like this. Okay, this one is upper part, lower part, upper part, lower part, upper part, lower part. Take note of that. So we just that is how postcode always is, unless you want to make it horizontal. So the postcode is most times vertical by default, but unless you want to turn it to horizontal, this is horizontal now. Okay, so it's supposed to be able to see properly. That's why we use horizontal method, so you can be able to explain properly. You can fill the page. All right. So median now is now less than mean. All right, and the upper quarter is larger than the lower quarter. So you can see that. So that is how we explain the normality, the box plot. So you can see that we have also what they call QQ plots. Compares the theoretical quantiles that the data should have if they were perfectly normal with the quantiles of the measured value. We have a theoretical value and we have a sample quantile. So in this plot now, you can see that this data, these are the observations. Okay, just dot observations, and they are lining on this line, so on this straight line, this up line, they're lining there. So if they have a perfect line like this, it means that the data is normally distributed like what it is. Okay, so okay, though you can see some little outliers here, out here and here. So a QQ plot is a very powerful plot also that shows outliers as well, like a box plot. You can see outliers out here. You can see right here. So you can even count sometimes some outliers if they are not too many. Okay, and if you look at this properly, you can see this one is you can see how it's curved like this. This one is not normally distributed. Okay, it's very obvious. It's not even along the line. It's out of the line, and it also shows some outliers from here out downward. Anything outside the line is outlier actually. So that is that about our data for now. So we are going to go to practical session, which is the second part now. And if you have any question, you can ask or post. And I thank you so much for listening to this session. I will see you in the next class. Thank you.